Hello, chemistry students. We are now ready to finish our topic on gases, and so we are going to turn our attention now to gas, wait for it, stoichiometry. And so I don't want you guys to panic. Please don't get panic. We are going to talk just a little bit again about stoichiometry, and so this section is not too bad, but I do want to talk a little bit about how we can use stoichiometry when it relates to things that are in the gaseous form. And so a couple things we'll be talking about today: what stoichiometric ratios can be determined for gaseous reactants and products from balanced chemical equations, and also how are the amounts of gaseous reactants and products in a chemical reaction calculated. And so as you can imagine, we are going to be having a little bit of math. And so let us go ahead and get started. All right. We are going to talk again about stoichiometry. I do want to also point out yet again, on the test there will be a problem that does involve gas stoichiometry, and I will always provide you guys with the balanced chemical equation. And so here's an example of a chemical equation that's been balanced for us. We have the hydrocarbon called methane combining with oxygen. So again, this is a type of combustion reaction. And so our two products, as always, are going to be carbon dioxide and good old water, H2O. And so I'll let you guys go ahead and see that this is in fact balanced out. The atoms balance out on both reactant and product side of the equation. All the laws that we have learned so far involving the gases can be applied to calculate the stoichiometry of reactions in which the reactants and products are gases. And so it applies to this just as well. Again, we're going to be looking at the coefficients. And so as you guys will hopefully remember, the coefficients are the numbers out in front of the different species of a reaction. And so as you remember, we know, for example, that a molecule of methane will react with two molecules of water to form a molecule of carbon dioxide and two molecules of water. In addition to this, we can also use the coefficients then to tell us the relative mole amounts that are also involved in this reaction. So we could also say that 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. However, in the case of gases, we can also use the coefficients to tell us the relative amounts of volumes of gases. And so we can say, for example, that 1 liter of methane reacts with 2 liters of oxygen to form 1 liter of CO2, carbon dioxide, and 2 liters of water. So again, by having the balanced chemical equation, it not only tells us the number of molecules that are involved, it will also tell us the number of moles that are involved. And now we can see, in the case where we're dealing with just gases, it also tells us the number of volumes involved as well. And so again, 1 liter of methane plus 2 liters of oxygen will form a liter of carbon dioxide and 2 liters of water. And so we can, again, use the stoichiometry to tell us that. All right, let's take a look at one of 2 examples. This first example is only going to be involving volumes. And so we're going to start here. In your home, or perhaps outside on your deck, you might have a grill that runs on propane gas. And so propane has the chemical formula of C3H8. We can take propane, we can combust it with oxygen, and yet again we'll see that we end up forming the same products. We end up forming 3CO2 plus 4 water. And so the question for this first problem: what volume of oxygen gas is needed for the complete combustion of 4 liters of propane gas under constant pressure and temperature? So I'm going to go ahead and refer you now over to the board here. And so, I apologize for that. And so we're going to go ahead and look at this first problem first. So here's our balanced equation up here. And so again, the question: what volume of oxygen is needed for the complete combustion of 4 liters of C3H8, otherwise known as propane? All right, notice that we're looking for volume and we're starting with volume. And so this is very much like doing a mole to mole conversion. And so if you remember from a couple chapters ago, in order to do a mole to mole conversion, you needed to know the mole ratio from the balanced chemical equation. And so now in this case, instead of having a mole ratio, we're going to be having what's called a volume ratio. And so again, we turn to our balanced chemical equation in order to determine what that volume ratio is going to be. So notice we're starting with 4 liters of C3H8. So we have 4 liters of C3H8. We need to now determine the volume ratio. We again look at our balanced chemical equation. You will see that we have 1 liter of propane, C3H8, that's reacting with 5 liters of oxygen gas. And so we are going to use this relationship then to figure out the volume of oxygen that's needed. And so notice that we'll put the 1 liter of the C3H8 on the bottom and the 5 liters of O2 therefore goes on the top. All right. And so without using a calculator, I can go ahead and determine that 4 times 5 is 20 liters of O2. Notice again, in order to do this problem, I had to use the balanced chemical equation, which will be provided for you, and I noted that there's 1 liter of C3H8 that reacts with 5 liters of O2. This is my volume ratio. I put the 5 liters of O2 on top. The 1 liter of C3H8 goes on the bottom. These 2 units cancel out, and so when I take 4 times 5, I end up calculating that I will need 20 liters of oxygen gas in order to have this completely combustion. All right, and so let us now turn our attention toward the second type of problem. And so our second problem here is in regards to the production of ammonia. And so ammonia is used in fertilizers, and it's used therefore to help in the promotion of the plant growth. All right, here is our balanced chemical equation. Our question: if 5 liters of N2 reacts with H2 at 3 atmospheres and 298 K, how much NH3 is produced? And so this problem, there's actually 2 parts to this problem. And so the first part involves finding first the volume of NH3 based upon this. And so then we can then determine then the amount, which is in grams of the NH3 produced. And so we're going to go ahead and also use the ideal gas law. The second part will then be used then to determine what the mass is. And so what we're going to do, we're going to go ahead first and calculate how much ammonia gas as a volume is produced. So just like the last problem, we're going to go ahead and start off with 5 liters of N2. We look at our balanced equation. We note that we have a liter of nitrogen gas reacting with 3 liters of hydrogen gas to form 2 liters of ammonia, which again is NH3. So again, we need to figure out how much ammonia is produced volume-wise. We're starting with nitrogen. We have 1 liter of nitrogen. We have 2 liters of ammonia being produced. And so we'll put the 2 liters of ammonia on the top and the 1 liter of N2 goes on the bottom. And again, not needing a calculator, I can see that 5 times 2 is 10 liters of ammonia. All right, and so we've now completed the first part of this problem. So we've determined that there's going to be 10 liters of ammonia gas that's produced. Now what we need to do is determine, based upon the other information then, what the moles are going to be. And so because we're given the volume here, we know the pressure, we know the temperature, and so again we're going to be using the ideal gas law, and so we're going to be looking for N. And so based upon that, then we can calculate the grams. And so let's go ahead and do that. Just like before, in order to make things simpler on myself, I'm going to go ahead and move the R and the T over to the other side by dividing each side by that, and so that I can set up N by itself. So I know that N is going to be equal to PV times over RT. So P times V divided by R divided by T. And so that will then set this up for that. So I need to now solve for the number of moles. I'm told in my problem that the gas is at a pressure of 3 atmospheres. So I'll go ahead and put 3 atmospheres for the pressure. The volume we have now calculated for the ammonia is 10 liters. So we'll use this number and we'll plug it in right here. We will also then need the gas constant. And so remember, the gas constant depends upon the pressure unit. Notice again, we're using atmosphere, and so our gas constant this time is going to be 0.0821 liter atmospheres per mole K. Again, I will give you the 3 gas constants on the test. You do not have to memorize that, but I'm going to go ahead and put that in now. And so we're going to have 0.0821 liter atmospheres per mole K. And then finally, we're told that our temperature of our gas in this case is 298 K. So fortunately, we don't have to convert from Celsius to Kelvin. It's already provided us for it. So we'll put the 298 K here. All right. We're going to go ahead and solve now for N, which again, as you remember, is the number of moles. And so we're going to go ahead and plug this into our calculator. And so we're going to go ahead and take 3 times 10 on top, and we'll divide by 0.0821 and divide also by 298. Oops. And so when we do that, we're going to find out that we're going to get approximately 1.2 mole of the substance. And so we are ending up with approximately, let's say, we'll say 1.23 mole of the ammonia gas. And so let's go ahead and write that down. All right. Notice, however, the problem is looking for what? It's looking for how much NH3 is produced. So it's looking for the mass in terms of grams. And so notice we have mole, we're looking for grams, and so what would we need to use in order to do this? We need to know the molar mass of ammonia. And so let's go ahead and calculate that next. We have and remember that in order to calculate the molar mass, we're going to use the atomic masses from our periodic table. And so you will always have the periodic table to use at your disposal. Notice we have 1 atom of nitrogen in ammonia, and we have 3 atoms of hydrogen. And so the nitrogen is going to weigh approximately 14 grams per mole. Each hydrogen is going to weigh 1 gram per mole, but notice that we have 3 of those. And so in order to calculate this out, we're going to take 14 grams per mole plus 3 times 1 gram per mole. And so you will see that the molar mass of ammonia in this case is 17 grams per mole. And so now that we have the mole, we have our conversion factor, we're just going to go ahead and take 1.23 mole of NH3, and we're going to multiply that. And so we need to put the 17 grams on the top so that the 1 mole can then go on the bottom so that the units can cancel out. And so we have 17 grams of NH3 for every mole of NH3. All right. To solve this problem finally, we're going to take 1.23 and multiply by 17. And so when we take 1.3 times 17, we're going to end up getting something that's going to be, I'm going to say, roughly 21 grams. And so we're going to end up forming roughly 21 grams of NH3. And so this is our final answer. And And so notice that for this problem, and it did involve two parts, the first part was to first determine how much ammonia gas was produced, and so based upon our 5 liters of N2, also based upon our balanced chemical equation, we were able to calculate that there were 10 liters of ammonia that were produced. Then we can use the ideal gas law in order to calculate the number of moles of ammonia gas that are involved. And so we plug in what we're told. We end up getting 1.23 moles of ammonia. And so by calculating the molar mass of ammonia, which turns out to be 17 grams per mole, we take 1.23 mole, times it by 17, and we end up calculating that we should end up forming 21 grams of ammonia in this reaction. All right, and so what I'd like you guys to do then, go ahead and do the homework problems that are assigned for this section. And so I hope you guys have a good rest of your day, and I hope to talk with you guys again soon.